Welcome to a new video on my channel. This is Machine Learning Series. In today's episode we are gonna have a look at Rdge Regression. In the last episode we have talked about LASSO regression. Also I have tried to give a gentle introduction into the topic of regularization, since regularization is not easy to understand in depth. Superficially it might seem very simplistic, but it is actually not. Today we will talk about one caveat that we didn't talk about in the LASSO episode. Just a small recap, we have included to our objective function another additive loss component that is proportional to the L1 norm of the weights, so we penalized weights for becoming too large. LASSO helps us to select the relevant features and would try to set other weights associated to unnecessary features to 0. Rdge regression does something similar. Instead of utilizing a L1 norm penalty, we will instead use an L2 norm penalty. But when you have a look at the Rdge term, you will notice that it is not proportional to the L2 norm, but to the L2 norm squared. That is correct. The reason is that squaring has the following benefits. First of all, it simplifies the mathematical computations involved in optimization. The resulting objective function is convex. Secondly, the squared penalty term results in a smooth regularization term. In this way, we include all features while shrinking the coefficients. LASSO could zero out some weight components, which will not lead to exactly 0 weight components. And the third reason is that the squared term penalizes larger coefficients more heavily. The shrinkage effect will become larger towards 0, but not exactly 0. Now here's the caveat that I didn't tell you about in the LASSO video in order to not confuse you from more than you already should be. When we do regularization, we actually leave out the bias term from the regularization term. We didn't do that in the LASSO episode, although we should have done it. You may ask, why shouldn't we include the bias term in regularization terms? Well, there are 3 main reasons. The first reason is the bias term is independent of any feature. It is simply an offset that shifts our model prediction up and down. But we do regularization because we want to prevent our model from overfitting, meaning that our model should not follow the noise inherent to our training data too close. But changing the bias term will not lead to a better generalized fit of our model. Secondly, it can make the interpretation of model predictions more difficult. Suppose the optimal model has a bias of 3, but due to our regularization term we shrink it close to 0. So our bias term would essentially have no meaning anymore since we are artificially drove it close to 0. And the third reason is that we may introduce collinearity issues, meaning that one feature can be predicted with the help of the other features. But we prefer to have orthogonal features, or so to speak, a model that includes only relevant features that are independent from each other. So, is it wrong to include the bias term in the regularization? Well, that is why we have included it in the LASSO episode, because I wanted to teach you here that it's not black and white. It depends on the goal. Technically, it is not wrong. However, it's important to carefully consider the implications and trade-offs in terms of interpretability, computational efficiency, and stability. There are regularization techniques where you include the bias term, but conventionally we don't do this in LASSO and Rdge regression, due to the previous mentioned issues. So, enough about this issue. Let's move on. So you remember how involved the computation of a gradient in the LASSO case was, right? In Rdge regression, it's simpler. The result is simply 2 times lambda times the weight vector transposed. One consequence from that is that the larger our weights become, the higher the gradients of loss will be. Also note that we only apply the regularization term during training. Finally, we have spoken all the time about linear regression and regularization, which meant to prevent overfitting. But how can a linear model overfit? Well, let's find out. So you can see here a feature x1 and a dependent variable y with only 2 data points. When I would ask you to fit a linear model to this dataset, how would you do that? Well, you would probably take a ruler, put it down such that both points are on the ruler, connected, and then draw a line. This is also what our machine learning model will do when having only 2 points available, as can be seen here. At least when we train our model with the mean squared error objective function. In this case, our linear model is overfitting to our training data since it has no other choice. That's why one can say that this is a degenerate case, since we artificially force our linear model to overfit. That's not something that would normally happen in reality. But as an example, it will do. So if a number of features that are independent variables are large relative to the number of data points or observations, we can observe overfitting in linear models. It doesn't mean that our linear model will necessarily overfit, but the probability is there. What we also can see is that our regularized model is not following the 2 points, since our regularizer hinders our model to get too close to those 2 data points. So the red line is the fit with the mean squared error objective function, and the green line is the one with mean squared error plus the Rdge term. However, we cannot really say whether this is good or not, since we got only 2 data points, right? But for the fun of it, let's add more data points to it and see how our models would perform in this case. So now we got 6 data points, and the loss of the model that was trained with mean squared error is approximately 174. And the loss of the model that was trained with mean squared error plus Rdge is approximately 142. Remember that we only use the regularization term in the objective function during training, so here we are only applying mean squared error to our model prediction in order to assess the loss. So indeed our model that was trained with mean squared error plus Rdge performed better. But as I said before, this is a very degenerate special case. This could be pure chance that our mean squared error plus Rdge performs better than the model which was only trained with the mean squared error. But suppose you would include polynomial terms in your model and would have more data points. When your model is too complex, it could be that it will overfit the training data. For instance, the cubic term might become dominant in our model. Rdge regression would suppress this behavior, possibly leading to a more linear form if the data is rather linear. This could improve the loss in the end and help us to generalize our model better. So before we end this video, let's have a look at the code and how to code up Rdge regression. So this code, we already used a very similar version in the last episode in the LASSO regression. But in this case, we apply Rdge regression to it. What was the Rdge term again? Well, it was equal to a coefficient, which we call lamp, times the L2 norm squared, right? This is what we got here. But remember that we are leaving out the bias term. This is why we have included the 0 here. And this is why only we compute the L2 norm for all the rates except the bias term. Because then when we compute our combined mean squared error objective function, then we have the mean squared error plus the Rdge regulator. For the bias term, it will be 0. And this is what we wanted, right? So as you can see, we have to do a slight modification in order to achieve our goal. And for the gradients, you have to do the same. It is 2 times the weights vector times lambda, right? This is what we got here. And here we do the same. We are only using the weights up to the last element, because the last element here is our bias term, and this is again 0 because we are leaving it out. Simple as that. If you are motivated enough, try to implement LASSO regression again, but this time with the conventional approach of leaving the bias term out. I hope you found this video insightful and helpful. Please like and subscribe. And if you have ideas for other videos that are interesting to you, write them down below in the comments. Thank you and see you the next time.